In December 2015, SpaceX achieved a groundbreaking milestone by successfully landing an orbital Falcon 9 rocket booster back on Earth, a feat never before accomplished in human spaceflight history. Fast forward 8 years, and SpaceX remains the sole provider capable of achieving this remarkable feat, with no one else even attempting it. But what's the secret behind this extraordinary success? Is Elon Musk truly a super genius of unprecedented proportions? While that's a possibility, we believe there's a far more captivating and gratifying story to unveil. Join us as we delve into how SpaceX reinvented the rocket industry. The defining factor that sets SpaceX apart from the rest of the aerospace industry is its groundbreaking approach to reusable rockets. While you might think that someone else must have considered reusing gigantic rocket boosters before, the reality is a bit more complex. Let's dive into the details. Back in the early days of space exploration, the first rocket boosters were essentially modified intercontinental ballistic missiles. For instance, the Titan II served as the launch booster for NASA's Project Gemini. However, these early rockets were not designed for reusability, and most of their components were discarded after use. When NASA embarked on the Apollo missions to the Moon, they developed the massive Saturn V rocket. Surprisingly, despite its immense size, only the small crew capsule at the top was designed to return to Earth. The rest of the Saturn V was left either floating in space, dumped in the ocean, or abandoned on the Moon's surface. This may seem wasteful, but at the time, it was more cost-effective than developing a fully reusable rocket. Engineers believed that building 12 disposable rockets would be cheaper than creating just one reusable one. However, NASA was already looking ahead. Even before humans landed on the Moon, they were developing the concept of the Space Shuttle, a fully reusable spaceplane and booster system. This concept, initially called the Fairy Rocket, was designed to bring human spaceflight into the mainstream. The idea was to have a 3-stage rocket, with the first 2 boosters returning softly on parachutes, and the third stage, the orbiter, gliding back to Earth for a runway landing. Now, you might wonder how this differs from the space shuttle we eventually saw in action. Well, while the space shuttle was generally considered reusable, it was more accurately refurbishable. After each flight, the entire system required disassembly, inspection, servicing, and reassembly. This process took a substantial amount of time and effort, making it less economically viable for frequent launches. So, what sets SpaceX apart? The key lies in truly reusable rockets that can be rapidly turned around for the next launch, similar to how commercial airplanes operate. NASA's Space Shuttle didn't quite achieve this level of efficiency due to the extensive refurbishment required. The question remains, at what point does a reusable rocket become economically viable? NASA never got the chance to answer this question due to the Space Shuttle's limitations, cost overruns, and infrequent launches. Then along came SpaceX, determined to succeed where others had faltered. Their approach to reusability was markedly different from NASA's, and it made a lot more sense from a logistical standpoint. From the very beginning, SpaceX had a vision of recovering and reusing both the first stage booster and the upper stage of their rockets. Their plan involved executing a propulsive return to the launch site and a landing maneuver. While SpaceX initially considered recovering the second stage as well, they abandoned this idea early on. It was a reasonable concession since the second stage of a conventional rocket is relatively simple, consisting of just one engine, a few small fuel tanks, and a platform for payload deployment. Recovering the first stage booster, on the other hand, held tremendous value, provided it could be made fully reusable, not just refurbishable. SpaceX decided to take on the most technically challenging method of recovery, propulsive landing. This approach was unprecedented. In contrast to Wernher von Braun's concept of booster stages using engines for deceleration before landing in the ocean, SpaceX aimed to perform a propulsive landing. This involved the booster stages landing vertically with the help of their engines. Why didn't SpaceX opt for parachutes, you might wonder? They did try parachutes, but physics got in the way. Parachutes worked for the Space Shuttle's solid rocket boosters for 2 reasons. First, they were relatively small and light, being solid rocket boosters. Second, they separated at a lower altitude and a lower velocity, around 3,800 kilometers per hour, compared to the Falcon 9's much higher and faster stage separation speed of over 8,000 kilometers per hour. The Falcon 9's booster had to impart a significant amount of velocity to the upper stage to reach orbital speed. This meant that the booster carried an enormous amount of kinetic energy, making it impossible for parachutes to slow it down sufficiently. SpaceX followed Elon Musk's philosophy. The best part is no part. Since the rocket already had engines, there was no need to add parachutes when the engines could do the job better. Moreover, the Falcon 9's engines served another vital role as a free heat shield, protecting the booster during re-entry. As the booster re-entered Earth's atmosphere, it would flip around and point its engines in the opposite direction to perform a re-entry burn. This burn would slow the booster down and create a protective force field underneath it, shielding it from the extreme heat of re-entry. The result was the spectacular jellyfish cloud of smoke and fire seen during re-entry. As the booster descended through the atmosphere, it would lose more velocity due to friction and would be guided by aerodynamic grid fins. At the last moment, the engines would reignite to bring the booster's velocity to zero, just as the landing legs touched down on the floating platform. SpaceX didn't achieve this feat overnight. It took a lot of trial and error, along with multiple upgrade cycles, before they perfected the Falcon 9. The rocket went through several iterations, with the final version being the Block 5, established in 2018. Unlike most rockets that remain unchanged once in operation, SpaceX actively developed and improved the Falcon 9. The original Falcon 9, known as version 1, was smaller and less powerful, with no provisions for reusability. SpaceX wanted to ensure it could successfully launch before focusing on recovery. Version 1 flew 5 missions, including sending a cargo Dragon capsule to the ISS. The Falcon 9 version 1.1 marked significant growth, both in size and power. With the introduction of the Merlin 1D engine and the circular OctaWeb engine layout, its total thrust increased to 1.3 million pounds. This version was the first capable of a controlled return to Earth, thanks to its enhanced size and power. As SpaceX continued to iterate and improve the Falcon 9, they gradually transformed it into the fully reusable rocket we know today. SpaceX's journey into rocket reusability began with meticulous experimentation and gradual development, aiming to achieve what was once considered an audacious goal: creating a truly reusable rocket. Their approach involved a series of carefully planned steps and innovative solutions, setting them apart as pioneers in the aerospace industry. In April 2014, during the CRS-3 mission, SpaceX took a significant step by equipping the Falcon 9 rocket with its first set of landing legs. This marked the initiation of their pursuit to master the art of rocket recovery and reuse. These initial tests were instrumental in understanding the challenges of bringing a rocket stage back to Earth safely. Following the installation of landing legs, SpaceX continued to refine their reusability techniques. In January 2015, during the CRS-5 mission, the Falcon 9 received its first set of grid fins. These grid fins played a crucial role in achieving more precise control during the freefall phase through Earth's atmosphere, a crucial step in successful rocket landings. With growing confidence and experience, SpaceX set their sights on a daring objective: drone ship landings. Although their first attempt on the same CRS-5 mission didn't result in a successful landing, it demonstrated that SpaceX was pushing the boundaries of what was previously believed to be achievable in rocket reusability. It's important to note that none of the version 1.1 Falcon 9 rockets successfully landed. In June 2015, a Falcon 9 rocket experienced a mid-air failure, prompting SpaceX to temporarily suspend operations. This setback, however, provided valuable lessons and underscored the need for further improvements. SpaceX returned with Falcon 9 version 1.2, known as Falcon 9 Full Thrust, which represented a significant leap forward. This version was slightly longer, reaching 70 meters in length, and delivered a substantial increase in power, with a total thrust of 1.7 million pounds. The key innovation that contributed to this power gain was SpaceX's groundbreaking approach to cooling their liquid oxygen and rocket fuel to lower temperatures, increasing energy density and overall efficiency. A pivotal moment came with Falcon 9, full thrust's historic achievement, the first successful landing of an orbital rocket booster. This achievement was a testament to SpaceX's dedication to pushing the boundaries of rocket reusability and demonstrated that it was possible to recover and reuse rocket stages. SpaceX's journey continued as they fine-tuned their approach, leading to the development of the Falcon 9 Block 5, the pinnacle of their reusability efforts. While maintaining the same size and only slightly increasing thrust to 1.8 million pounds, the Block 5 featured critical upgrades aimed at enhancing reusability and reliability. One of the key improvements was the modification of turbopumps in the Merlin engines to address micro cracks observed after launch and recovery. Additionally, SpaceX upgraded the grid fins, switching from aluminum to titanium for greater heat resistance and improved control during descent. The entire Falcon 9 received a thermal protective coating to reduce heat absorption during re-entry. Furthermore, a new, reusable liquid-cooled heat shield was introduced to protect the engines and plumbing system. The landing legs were upgraded to allow both extension and retraction, enhancing the overall reusability of the rocket. SpaceX also addressed a significant issue related to composite overwrapped pressure vessels, COPVs, which had been linked to previous Falcon 9 explosions. These COPVs, used to store helium gas for maintaining pressure inside fuel tanks, underwent improvements to enhance safety and reliability. As of the summer of 2023, SpaceX has made remarkable progress in achieving rocket reusability. Booster B1058, originally designed for up to 10 launches and landings, has successfully completed its 16th flight, surpassing initial expectations. This achievement showcases the Falcon 9 Block 5's exceptional reusability, which has the potential for even more launches and landings based on rigorous testing. With this impressive track record, SpaceX continues to push the boundaries of rocket reusability, making significant strides toward more sustainable and cost-effective spaceflight. As they set their sights on the next frontier with Starship, the world eagerly anticipates further groundbreaking advancements in reusable rocket technology. As SpaceX continues to redefine the possibilities of rocket reusability, what do you think Elon Musk will introduce next for SpaceX? Share with us in the comments below. And if you enjoyed this video, show us some love by hitting that like button and leaving a comment down below. Also, if you're a fan of all things technology, be sure to check out this other video we've got lined up for you. It's packed with all the latest news, tips, and tricks to keep you ahead of the curve.